I'm Greg Paulsen, and I want to talk to you about what to expect using the same 3D CAD model and different 3D printing processes, both in plastic and metal. So we used a model of a wheel with treads on the outside to show you how different processes turn out. You're going to see very distinct differences between each one of our processes, and we're going to talk about some of the reasons why. This part was printed using fused deposition modeling, where an extruded filament zigzags back and forth, growing apart from the bottom to the top. You can see very gradual steps on any curved surface. You also will see a little bit of that zigzagging on both the top and the bottom. You could still get some very clean results if you have the right gap width and the right geometry based off the direction of build. So for example, these parallel lines here came out very, very nicely. We use a dissolvable support structure, so we are able to get some of these smaller details by filling it in with support that's removed later. This part is very lightweight because I used a sparse infill on the inside, so we call that the ultralight infill. FDM can get some great details, as you see on the tread, but it does sweat the small stuff. In this case, we have a really, really fine ridge in the middle of the Xometry X, and you can see how, as it's trying to fill in, there's little air gaps there. This piece was constructed using selective laser sintering, SLS 3D printing. This uses a fine layer of powder and fuses it with a laser, growing apart from bottom to top, and it's suspended in powder so it can actually grow overhanging features without the need of support structure. We've media tumbled this to get a little bit of a smoother print, and we dyed it black. The fine line on the X did resolve, but it is thicker than what the CAD has it to be, and that's because the laser will heat up that powder around it to kind of over thicken the features. So expect my small gaps and even thin walls to be slightly thickened up just because of the nature of the process. Overall, for this geometry, the layers did turn out great, and even on the side here I have some really, really great resolution of the treads. This is a really cool use of PolyJet 3D printing. In this special case, I separated the shells using 3D modeling so I can assign a different material to this part. I chose our multi-material option using PolyJet, and I put a rigid white interior and softer durometer rubber-like on the outer tread. So this is great for a feels-like prototype where you want that tactile representation of what the part is actually going to be. Note that PolyJet can get some very fine details, and this is some of the most true to CAD geometry that we get. I did want to note though that even though small features do resolve, they are very fragile. So in this case, the actual lines on the X did resolve originally, but as we cleaned them, they blew away because we're actually cleaning this with a high-powered water jet. That's something to expect out of PolyJet because of the brittle nature of the process. So we always recommend keeping a minimum width of wall of at least 1.5 millimeters. This part is made with direct metal laser sintered aluminum. It's a very versatile material. It's lightweight, and you get some really unique geometries out of this. So something to notice is that this part was built as if it was sitting on the table. That means the parts facing up ended up having cleaner looking geometry, although because it has a laser essentially melting a powder, you do get some of that mottled nature, which is actually a splash that happens with the melted material. On the side though, the treads look a little rough, and that's because these were built unsupported. So as this part was built, there was nothing holding underneath these small features, and that's just literally where material was not fused to the rest of the part. Support structure was removed from the back, and you can see it has a much smoother finish, and that's from hand finishing or machining. Overall though, the natural print, either a sugar cube like finish or kind of mottled orange peel look to it. The X did resolve, and similar to SLS, those little lines are slightly thicker than what the CAD would originally have to it. So this beautiful piece here is made using binder jet 3D printing metal. And this is a two-stage process where first a green part is made by printing a binder on stainless steel, and then afterwards the whole part goes through a kiln and bronze is actually infiltrated, burns away the blue binder, and builds up about 40% of the part, which is why you kind of see that silvery bronze look to the piece. The part is then media tumbled as part of a standard finish to give a slightly glossy look. And since it has a two-stage kiln process, it does come out slightly smaller than the original CAD design. Compared to our other parts, you can see that the natural size is smaller. Overall detail resolution did come out, but we typically recommend about 30 thousandths of an inch or higher as a wall thickness. You can find many 3D printing processes are just as viable as traditional manufacturing to get your parts made, not just for one-offs, but even for full production. So for a quick reference, we have a blog post and a downloadable poster that you can take a look at to see details between these different 3D printing processes. I also recommend checking out our design guides for process-specific design tips that are going to help you get a part that you want the first time around. At Xometry, we have both 3D printing and traditional manufacturing services with instant online pricing. You can take a look for yourself and see what best fits your project needs by cost, lead time, and the properties of the materials that we can make.